as indicated on the title, this is a talk covering deep learned iterative PET image reconstruction, just covering some of the principles of how to do that in Python and PyTorch. So I guess I'm open to interruption as I go along with any questions. Maybe it's simpler to do that. I understand I've got about half an hour, and let me just check the time. Okay, so we finished about 1 o'clock. So one slide on how I perceive deep learning. Basically, it is software which learns from data. Normally, we explicitly code things up. We use physics laws. We use all kinds of analytical methods to write code. But with deep learning, we say instead, we know what output we want. We know what inputs we have. So given an input, we know the output, but we don't know how to code it up. Conventionally, image reconstruction, we would analytically, I've got a very crude filter back projection algorithm written there. Normally, you would say, okay, well, I Fourier transform all the rows, I do a ramp filter, inverse Fourier transform, then I back project, and that would give me a reconstruction. So that's analytic, our knowledge being used to write code. Whereas, as implied, well, in fact, this is where we're heading, I'm viewing that code as a series of operations, a series of operators that normally we code up, okay? Now, this is where we get the concept of deep learning, is that we're doing, if you like, operator after operator after operator. And so that's where we get the concept of depth from. And the learning is because all we're going to be doing is providing example inputs and example outputs, and then learn what those operators need to be in order to get from the inputs to the desired outputs. So hence, on this rather different example of a kingfisher, imagine writing code that could identify a kingfisher. That is a very complicated piece of code. Whereas, if, of course, if you have example pictures of a kingfisher bird there, then you could say that is a kingfisher, and then you could just learn a cascade. Now I'm kind of going from left to right rather than top down there, but a cascade of convolutional operators that just learn various features in kingfisher images, such that we end up in a so-called latent space representation, which we could then do a linear regression from and easily classify this rather complex image. So deep learning then is what I like to consider as trainable code. Instead of us hardwiring code, we build in flexibility into the code and learn parameters for those operators. So that's my one slide on deep learning. Just to emphasize the concept of depth and the fact that we can build up this hierarchical representation. Maybe one other comment to add some insight here. Imagine this image was a collection of atoms. Then what we could do is, in the next layer, group those atoms together to form molecules. In the next layer, we could group molecules together to form materials, and then group materials to form objects, and so on. So we have this depth, this growing hierarchy of features. Anyway, so how do we apply this to PET reconstruction? Well, this is my one slide on PET reconstruction. You've already covered it. Chris has covered that nicely earlier. So we have some relativity distribution. Inside here, a PSMR scanner. We collect maybe 1,000 sinograms, and then we'd use either very old school filtered back projection or even still quite old ordered subsets EM in order to deliver a reconstruction of a representation of the object that was inside that scanner field of view. And similarly, for MR, you've got some net transverse magnetization inside that scanner field of view. You collect your K space. You could do inverse Fourier transforms or solve a least squares problem or do compressed sensing, whatever it is, to get your reconstruction. So that's my one slide on reconstruction. Now we're going to talk about how we get deep learning embedded into our image reconstruction frameworks. So why do it, first of all? Well, iterative reconstruction, as we've seen already today, builds in our chosen imaging model, our physics, and also the Poisson noise model. So these are two very desirable things that we like about OSCM or MLEM. So it's a theoretically well-motivated algorithm for maximizing Poisson log likelihood, or the log posterior, as you saw earlier with what Chris presented. But the only part that is not ideal, you could say, is the prior, which indicates which images are more or less probable. Okay, so what we're going to do then is use deep learning. We can use deep learning to describe which images are more or less probable. And so that's where we talk about the idea of the image manifold. And what I mean by an image manifold, here is a very arbitrary example. You saw earlier in Chris's presentation, we had this two-dimensional grid representing, points representing images. I've gone as far as a 3D grid here. And I'm just saying that various so-called manifolds, if you like, just parts of that high-dimensional space, correspond to different kinds of images. There I've got a representation of a manifold that would correspond to natural images of, say, the River Thames. I've got another manifold for MR images. You'd have another manifold for PET images. And the point is that normally our priors are way too vague. Total variation, MR guidance, these are relatively broad manifolds that accept a whole load of images that maybe are not really feasible. Okay, so we're going to put deep learning using these kind of image manifolds into reconstruction. The motivation will be that we're not going to be training an entire reconstruction network. We're going to keep the conventional EM framework and just build in deep learning for the prior. And therefore, we don't need that many training images, and it's going to be practical for 3D reconstruction. Although today we're going to emphasize 2D reconstruction with the project this afternoon will be 2D reconstruction. Okay, so some references there, which I think time will not allow me to go into. So there's the physics of the acquisition. I won't go into that in any great length, just saying you go from an image to a model of the mean of the data that you would have acquired if that image had been inside the field of view. So we have positron range, we have good old line integrals there. That's the so-called X-ray transform or radon transform, obviously discrete version here. Then we'd have attenuation, then we'd have normalization, scatter and randoms, and that builds up this affine transform, this basically system matrix plus offset, system matrix operating on your current image estimate to give a model of what the data would have been if that image had been inside the scanner. Now, let's now start to get towards PyTorch. So what I've done, you may have seen some of these videos already, is just to do a proof of principle of what you need to do. What I've done is create just the X-ray transform or the radon transform. I've just written that in Python and PyTorch. Now, this is a key principle number one, is that to use PyTorch, you're going to have to use torch tensors rather than NumPy arrays or whatever other objects you might have. So you've got to get all your code written in terms of torch tensors. And so all I've done here, I won't go into it in length. I refer you to a video that I think I'll link to that goes into that in length. What I've done is just calculate what that matrix A needs to be to forward model from a given image to a sinogram. And I've just stored it in a so-called torch tensor. So that's where I've got this torch.zeros, and it's a huge matrix, but it's still manageable in 2D. And so it would look something like this. So I've really exaggerated it here. There's my matrix A operating on some input vector, whether it's theta, whether it's X, to give a model of the mean. And that matrix would just be composed of, maybe this summary slide is good. It would just be composed of sine wave, if you like, responses to every single point source location for the columns. And then the rows of that system matrix would correspond to lines through the field of view. Let's now get to the iterative reconstruction that uses that forward model, whether it's just the radon transform or X-ray transform, or whether it's got all of those modeling effects in it. It's just that matrix A. And so you can see the matrix A just operates on an image X, and then you just compare your measured data to the forward model, and then you just back project it. That's the adjoint or the back projection of this ratio, which then gets multiplied by your image estimate to get the next one. And you need to just divide by the so-called sensitivity image, which just looks at how many back projection contributions there are to every pixel. So what we're going to do is take that algorithm and put it into a class to define a network, a deep learning network for that algorithm. We're going to unroll it, and I'll show you that hopefully in a bit more detail now. So first of all then, that process, which is, as you've seen, is forward project, ratio, back project, multiply, divide by sensitivity image. That's the so-called EM update. It takes the measured data, and then once you've done an EM update of some image estimate, you get a next update, you do the EM update, and so on. And so what we have for, say, a certain number of iterations is this cascade of operators, okay? And so that should be familiar to you. That's just a deep network, okay? So iterative reconstruction, if you don't do any learning, is a non-trainable deep network. So let's get this into PyTorch. So there I'm just showing the line integrals, because that's my simple system model that I'll be using here. So there it is. I mean, I've even gone to great lengths to make it as much as 5 lines of code there. But all we're doing is an iterative loop over an iteration number. And then we're just forward projecting using, so that'd be your forward model in Surf. Here it's just my simplified model. So I'm just doing forward project using a torch tensor for the matrix A. So we need a torch tensor based multiplication or operator on your image to give you the model of the mean sinogram, okay? Next line would be just simply taking the ratio. Next line is the back projection or the adjoint of the system matrix applied to that ratio, that corrective ratio. So you just back project the correction factors. We divide by the back projection of 1s. So that self.sense image is A transpose 1. And then we're ready to just multiplicatively update our image. So notice, this is line after line after line, a cascade of operators. It's a deep network. And so what we can do is take the simplicity of MLEM and just unroll it, as I'm showing there. I've just taken, there are many of those iterations. I'm just showing an example of how you take those 4 lines of that main loop and just place them as this cascade in a deep network. Okay, so then what we do is create a class in Python that inherits from the Torch NN neural network module. So that's going to enable us to make use of, remember what I had in those early slides, those convolutional operators. So there you have multi-channel kernels operating on multi-channel inputs, delivering multi-channel outputs. That's a lot of coding that we don't have to do. We can benefit from the Torch NN module. So that's why we have to initialize that module as well. But the core bit of that algorithm, I'm showing this entire slide is the entire class for that iterative algorithm is just what you've already seen. We have this forward method as part of that class. And you can see what I'm doing is initializing my reconstructed image with a torch tensor made up of 1s, okay, number of X samples, number of Y samples, and I'm putting it on the GPU, so .2 device. And then we're just running through iteratively those operations that I've talked you through. So hopefully you can see, hopefully now everybody in the room can take any iterative algorithm and write a class to represent that iterative algorithm, just unrolling it. In fact, here it's not even unrolled. It's still got literally the for loop there. Okay, but obviously supplying a number of iterations. So that's how you could take any iterative algorithm and just put it into a class. Right, so the observation I wanted you to make was that, well, maybe it was already written on the slide, but that had no trainable parameters in it, okay? So now what I'm doing is taking a classic convolutional neural network, which is another class in Python, where I'm making, again, use of the torch.nn module. So therefore, I can make use of its conv2D layers, which are those multi-channel kernels that can take in multi-channel inputs to generate multi-channel outputs. And all I've got here is taking in one image. So that means here I would have a 7x7 kernel operating on one image, and I would have 8 of those kernels, which means I get 8 output images. And once I've done those convolutions, you know, everyone hopefully knows linear shift equivariant mappings. Convolution is an extremely elementary operation. After that, we build in a nonlinearity, the parametric ReLU, that basically keeps positive values and just attenuates negative values. It's not as harsh as a ReLU, which would kill all your negatives. And then we just repeat that. But obviously, for the next convolutional layer, we've now got 8 channels coming in, 8 channels going out. So that means we'd have 8 kernels, and each kernel would have 8 channels. And because we've got 8 kernels, therefore we get 8 outputs. And here I'm using 7x7 kernels. The 3x3 padding is just to account for the fact that the edges I do want a pad with zeros so that the outputs are the same size in terms of X and Y as the input. So this is just, again, this is not a lecture on convolutional neural networks. Here I'm just showing a nonlinear shift equivariant mapping with obviously the nonlinearities built in there. Key thing is that these kernels are trainable now, okay? So now we can begin to present example data and learn what these kernels need to be for this CNN to map whatever we want to whatever we want. I mean, these are very expressive mappings. So there's the class, and notice again, it's got this forward method as part of that class there, where all I'm going to be doing is taking an image X, running it through my CNN to get the process output. And some of the subtleties of PyTorch are that if you want to use this NN module, then you've got to present your data in a 4-dimensional way. You've got to include a batch and number of channels. And if I've just got a 2D image, then I've just got to synthetically create those extra dimensions. And then once I've done that, I then want to squeeze it back to its original 2 dimensions to get my output. Right, so the shape of the input image here could be anything you like, okay? Because this is a convolution operator as effect. If you consider just one kernel, that can run over any size image you like. So you don't have to specify the size of the input image. Okay, the question is, how do we choose the shape and size of the kernels? And I would say the more analytic insight you can build into this, the better. So just for example, if you're doing filter back projection, if you know you're just trying to learn one convolution kernel to convolve each projection, then you should use a kernel of 2n-1 in size, just use one kernel, maybe build in a nonlinearity, and that would be a very viable network. If you're trying to learn more complicated image manifolds, then you'd have to use a sufficiently expressive and yet sufficiently constrained network that's capable, if you like, of only expressing that manifold. So there are no right or wrong answers here. It's a bit like when someone asks, how many iterations of OSCM do you use? It's a bit like that. It's like, well, it depends. It depends on your task. It depends on your training set, what you're trying to achieve. How risky do you want to be? How expressive or how constrained? But you should really think about a convolutional encoder decoder as basically encoding to some latent space. And you need to say, well, how many different kinds of feature am I really ultimately interested in? And so you could do it that way. And so in other words, if you're very confident, you're only looking for 5 different features or something, then you could really hardwire your latent space to be very constrained, a severe bottleneck. But yeah, a question from the 5th row. Yeah. So just to push the point again, if we wanted to be ultra conservative and always get it right, then we could just say our manifold just consists of smooth images. I'm only going to learn 2 or 3 kernels and very little can be done. It will all be safe, but too safe and you lose the power. And so it's all about, well, how far can I begin to press the complexity and still retain generalization for all the possible brains? And these are open-ended questions that are very task-specific as well. So I cannot, just like we couldn't tell you how many OSCM iterations to run, I cannot give you a definitive network architecture for your problem. But so these are really, yeah, these are the research topics and questions. Oh yeah, so once you've created, I didn't say this before, once you create your class, obviously you need to instantiate that as an object and we put it on the GPU so we get all kinds of speed ups. That CNN equals just that class instantiated to an object sitting on the GPU. Right, okay, so now then, I'm going back to that slide before where I had the unrolled MLEM architecture. All I've done is introduce those changes, which I hope you can just about see. I'm now passing a trainable CNN to my MLEM deep network that before wasn't trainable. So I'm passing a trainable function method, if you like, to it, trainable object, I should say, maybe. And then just naively, for the sake of demonstration here, I'm saying, well, what I could do is just learn what I need to add to my reconstruction in order to update it such that it matches a high quality reference. So here, if I had high quality reference data, I could just train up a CNN such that at every single iteration, exactly the same CNN operates on the current reconstruction to figure out what is the difference image that I need in order to add to my reconstruction in order to diminish noise, as an example. This is like a super basic putting a CNN inside MLEM as a network. And then, of course, you've got to instantiate that, as I'm showing at the bottom there. Right, so I won't go into much because time is really against us. So just to say that MapEM methods can also be unrolled networks where you have a data fidelity-based EM update. You basically have a denoising step that normally is based on your analytic prior. You know, that could be a weighted quadratic penalty, for example. And so the key point being that conventional MapEM methods, regularized EM methods, are nothing more than a deep cascade of operators. And so these can, of course, be put into a deep network. And there I've just shown that also the denoiser can make use of MR information. So that would be very much at the beginning today. Chris showed you a Bauscher reconstruction in SURF. So this would be an example of putting MR information into that denoising step in this so-called De Piero update that takes the data and also takes the MR information with the quadratic penalty to fuse them together to give you a regularized update. So here, again, is non-trainable iterative regularized reconstruction, not likely to be optimal because the prior is still too vague. And so what we would do, I won't go into it now, is do exactly the same class definition where we just write our iterative algorithm now as a class, including trainable components. In fact, for the denoiser, we'd put a CNN. Let me just show you that. What we do is take that structure, and that's what I'm showing here. What you could do is just put a CNN there to train up a prior image to do a very simple MapEM update with a quadratic penalty on that prior to get the next update and so on. And this is like a basic framework for a number of regularized unrolled iterative reconstruction methods. Key point is it's got a trainable CNN in there, which could be iteration dependent or could be the same for all iterations. Now, just to finish, how do we train up? Well, what we're saying is when we put in an initial image into that cascade of operators with noisy data, what I'm requiring is that that endpoint iteration needs to match regular MLEM, if you like, operating on very high quality data if you've got it. And then we're just saying that that top unrolled network, the endpoint needs to match the reconstruction of high quality data. That allows us to define a so-called loss function, where what we can then do is update the parameters of our trainable CNN in such a way that when we run that network, the output matches the high quality one. So this is where we take the gradient of the loss function. This is where we do what's known as back propagation, which is just gradient descent updating of the parameters of the CNN. So that's why you need this key last bit of code I'm showing you before I begin to wrap up. What you'll see, and if you do the project this afternoon, this is the kind of framework. All we do then is define, for example, here, mean square error loss function. Next line is define an optimizer. So that could be as naive as a gradient, a stochastic gradient descent method. Most of us use the Adam optimizer. It's a bit more sophisticated, momentum and other benefits built in, not monotonic though. And you give it a certain learning rate. If you like, that's like a step size. You can view that as a step size for a gradient descent based update. And all you do is supply it with your instantiated, your class that you instantiate as an object. It's got parameters that are trainable. So I've called it unrolled reconstruction network that has parameters. I tell the optimizer, those are the parameters I'm going to optimize, and I want to use the Adam optimizer. And the loss function is as defined there. And then all we do, a bit like doing an MLEM reconstruction, we just do iterations where they're called epochs. So analogy would be one epoch would be like one iteration, and a mini batch would be like a subset. If you like, deep learning, machine learning has different terminology for how you get hold of your data. But an epoch is like a master iteration through your whole data. So it's like one whole OSCM. It's not OSCM, but I'm just saying by analogy. One epoch goes through all of your training data. And what you do initially is you zeroize your gradients. Okay, those are the things that are going to be used to update the parameters, the trainable parameters. Then We get the output of our unrolled reconstruction network. We just supply the sinogram that we want to reconstruct, get a reconstruction output. Then we evaluate the loss. So that'd be, for example, the mean square error loss. We look at our current output and we compare it to whatever our high quality reconstruction is. Once we've got the loss, we could save it off here. This is very unnecessary. It's just for our information to save off the value of the loss function. Once we've found the loss function, we can then find the gradients of that loss function. Okay, so in other words, what is it that needs to be added or subtracted from each of the parameters in the CNN in order for when that network is used for the output to be closer to the one that we're specifying in the loss function. And here we're specifying, here I've got this true object, high quality reference as being the target in my mean square error loss function. So the gradients will tell us how to change the parameters to make that more true in each update. And then once we've found the gradients, we then, if you like, just like with gradient descent or MLEM, we just add on or subtract those gradients. And that's it. Obviously, there's a lot more work to be done. So the point is you just supply, just like with OSCM, you offer different subsets. Likewise, in this training loop, you can offer different mini batches of data pairs where you supply the measured sinogram and then what you expect it to be. Okay, that's the key pair of data points. Okay, just to show some results of doing the FBSEM network. And you can see it's just the EM update with just a convolutional network in parallel with it, with a fusion update, just based on conventional MapEM reconstruction. If we train up a CNN, then we get some very nice results. Here it's 77,000 parameters being trained from 35 patient data sets, and representative results are shown here. You can see the deep learned CNN as used in the prior, which basically is driving us towards that image manifold of feasible images for FDG PET. You can see on the far right side there, it's doing somewhat better than vanilla regular OSCM. And that's just a 2 minutes data, 2 minutes data on the right hand side. If we had 15 times more data, so the high quality reference is shown in that column there, you can see that it's doing a reasonably good job. Okay, right, I'm really out of time. So just to mention what will be done this afternoon in the project, here I've been talking you through unrolled iterative reconstruction, which uses our physics and stats and uses, just draw your attention to that second line, our known iterative image reconstruction algorithms. And notice I put a question mark there. Is that really a tick? Is that really what we want? Do we really want to use MLEM, MapEM? I know it's theoretically appealing and so on, but we don't know. We need to do an assessment, I guess. Is that the best way of doing it? Well, a query, it's a genuine query, because what we're doing this afternoon is going to be using the learned primal dual method, where all we do is, in fact, we just discard the whole idea of MLEM, and we just take an inspiration from the primal dual hybrid gradient method, which I won't go into detail now, because intuitively, what we end up with is something like the following, where we just take sinogram data, learn a CNN to process it, back project it, learn a CNN to process that, forward project that, learn a CNN to process that. So all we're doing is just taking effectively a whole bundle of CNNs, a whole bundle of forward and back projectors, in other words, trainable components with physics components, in order to get an endpoint output that matches what we expect. And so this is just the only time I've seen this at the moment on PET data. This is kindly a figure donated by Massimiliano Colarietti Tosti. But the work this afternoon will be based on the original paper by Adler and Optum. I think it was for CT data originally, although we'll be using Shep-Logan phantom, I think, as well as ellipses. And basically, it's a cascade of operators in the measurement domain, cascade of operators in the image domain, and we have forward and back projections linking between them. So it's more like just gluing together CNNs with physics. And the results, as shown, are seemingly better than conventional reconstruction methods. So you have a limited number of parameters to learn. We've got physics in there. And we've even now abandoned a it's a less explicit connection with a recognized reconstruction method. Obviously, it has links with primal dual hybrid gradient, but if you look at the changes, it's quite a departure. Really, it's as I just described it. It's almost an intuitive method inspired. So that's pretty much it from me. Happy to take any final questions.